Thanks for joining. I hope you find the webinar interesting. I'll just give a little background to myself. My name is John Edwards. I'm based in the UK, and in the 60s I worked at Imperial College in the biochemistry department, and then as a project engineer for the Foxtra company in Massachusetts, where I obtained an MSc in engineering management at Northeastern University. On returning to the UK in the 70s, I was a plant manager at Roman Haas on Teesside, and in 78 started my own company, P&I Design, for consultancy services. After semi-retirement in 1998, I took an interest in process simulation after seeing ChemCAD by Chem Stations demonstrated at an exhibition in the UK. And with my experience in process control, I saw the potential for dynamic simulation and have used this on many projects since. I provide courses for Chem Stations on dynamic simulation internationally, and have summarized this work in self-published books. Our main areas of activity are in chemicals, fine chemicals, bulk storage, combined heat and power, and carbon capture. We've found this to be an invaluable tool, and by demonstrating some of the applications, hope to show you the potential and benefits. So just a brief introduction there. My thanks to Daniel Hill, who works at P&I, and for David, who works at Chem Stations. And the presentation is based on a publication we did in the Chem process in 2019. So, just to kick it off, as you all know, if you're interested in simulation, which you obviously are, steady state is the most common method used, and dynamic simulation is not used that regularly. Steady state's very powerful because you can get sensitivity analysis and investigate interactions between parameters. You can do optimization. But dynamic simulation represents the actual process and equipment behavior in real or speed up time, and it can be applied to applications with no control and with process control. Now, this slide's trying to summarize the justification. We've used this in all the areas shown there. We did a project for someone in China who found it invaluable and saved him a lot of time on the laboratory side of things and reduced his experimental time considerably because we managed to model his laboratory equipment and make guidance regarding future experiments. Design, it's very powerful because it allows you to test your decisions regarding sizing and control systems, and it can alert you to problems maybe with turn down and interactions that you might not spot. Operations, again, we've been able to solve problems by modeling the process and identifying where problems occur and where they're coming from. And then on performance, it's powerful for doing optimization. You can, with a calibrated system, you can predict unmeasured parameters and identify process excursions. And it's applicable to a whole range of industries, not just batch processing, but continuous processing, emergency relief, safety case analysis, and even regular plant operations. Just a little cautionary tale. The graph, I think, is quite a common one. It states the obvious, really. If you find a problem early, you're going to save yourself a lot of money than finding it later on. And just a summary of some of the points there. So the first thing I'm going to look at is regular plant operations, because I find that people are reluctant to get involved with dynamic simulation because they don't feel they have the experience on the process control side. So what I'm going to show you here is 3 projects we did using dynamic simulation. The first one is a tanker offload. And basically what this project was about, we're going to transfer aqueous ammonia with some hydrogen sulfide from a road tanker, and we're then going to transfer it to a fixed storage tank. And the problem the customer had, he didn't have a balance line back to the road tanker. And what he didn't want to happen was to have this breather valve lift, because it had H2S in it. So we were asked to size this line. Now, you could say to yourself, well, we could size that line without even using any simulation. But what we found was, by doing the dynamic simulation, it allows you to study all parameters and interactions that are taking place on a system like this. So this is just for those people who haven't seen ChemCAD, but basically what we have here is we've got a dynamic vessel where we set up the dimensions of the vessel, we set up the mode of operation of the vessel, and over here we have the pipe sizing set up. Note that we can include the hold up in the dynamic simulation. We've got pump details where we use the pump curve, and we use nodes, pressure nodes. They're used to balance the pressures in pipe networks. I'm going to run you a real-time operation at the moment. So this is the setup of the dynamic vessel with the dimensions and the heat duties and everything. We're now going to identify the outlet flows. The outlet flow is determined by the pipe section or a control valve if you wanted. You could do a relief device, and that's the results at steady state start. We now set the pipe section up. Single phase flow. We're going to measure the P in and P out and calculate the flow. There's the dimensions of the pipe, roughage. Calculated results coming up. We can specify valves, and we can specify fittings as well. We can specify special valve situations there. Pressure node. Now this is setting the pressure balance. So we've got variable pressure, and the flow is set by unit op in, unit op out. And this varies as the simulation proceeds. We now go into the valve, which has got a performance curve set. We're going to check the net positive suction head available throughout the run. And then that's the performance curve from the manufacturer. We set the pressure node on the outlet. Variable pressure again, flow set by unit op, flow set by unit op. There's many variations on that. And then finally the storage tank. You see it's quite a decent sized storage tank, and it's set for flash with heat duty. And we've got an initial level set here as well. Outflows set here, there's no flow out. We've just set a 1 kilogram rate at the top initially, and then there's calculated results. And that's the storage tank contents at the start of the simulation. We're now going to run the dynamic simulation. And we can select what variables we want to look at during the simulation, and that's purely your choice. So I won't be showing any more of those because that's just to give you the feel for how we'd actually set up a simulation. Now we get the results. All these graphs that you saw have been exported to Excel. So in Excel we can combine graphs. We can, if we're looking at power consumption on a facility, we can bring all the power values in from pumps and agitators and summarized power. But here's the tank level. So this is the vessel. Sorry, this is the tanker. This is the vessel. NPSH available. See, we're okay here. As the tank's getting empty, obviously we've got a problem there coming. Tank pressure, we've stayed under the set pressure of the breather valve, and this is actually giving us the composition of the exhaust gas. The next one is bitumen storage. This is quite a tricky substance to work with because of the viscosities. And what we have here is basically we have the storage vessel, and we are circulating heat transfer fluid via two fired heaters into two coils in the tank in the reaction vessel here. It is a reaction vessel that we use. So we circulate through there, return here, and we circulate back round. With bitumen, when it's filled up with fluid from ships, it could well be that the temperature is low, and that could prevent us from offloading to a tanker. And we have another heat exchanger here, so we can recirculate through the heat exchanger and do quicker heat up. But we need to know how this behaves actually in the tank. So it's just to give you an idea of the problems we have bitumen viscosity varying quite considerably throughout the course of the operation. This shows you the data map that we use. Now we can connect ChemCAD to Excel via data maps. And what we're actually doing here is, so we can do data exchange between simulation, we can do data exchange with Excel. So for example here, we can send this spec to ChemCAD from cell C6, and we can send from the worksheet stream 5 the temperature, okay, to the worksheet, sorry. And what we're actually doing here is using correlations to work out the film coefficients for the heat transfer in the tank. So we can bring in our own calculations into ChemCAD. That's the plots that we've run in ChemCAD. This is actually done out of ChemCAD here, these plots. So you can see the reactor temperature here. You can see the jacket temperatures and coil temperatures here, in and out temperatures here. And basically the benefits was we could check operational changes, we could check fouling, we could see the performance with variation in ship offload temperatures. We can predict key physical properties, and just we can check general performance. This actually, I'm trying to demonstrate here the power of dynamic simulation. What we had here was the offload situation. So we're coming from the bitumen storage facility. We're through that external heat exchanger, which you can see is quite substantial. And then we're returning back to the bitumen storage. But the option comes when we're loading tankers, we come off this stream here. We're circulating heat transfer oil here to control the temperature coming off to storage. And what we found by running live simulations, that this is a three-way valve actually. We're showing it as two ways, but basically we found that this valve CV at 140, we couldn't control the temperature appropriately when we were doing tanker offload. So by doing experimentation with the dynamic simulation, we decided we needed to add a trim valve, excuse me, at CV16, and that solved our problem. This is the just plots showing you some of the overall heat transfer coefficients that we got, shell side DP that we had, and this is the behavior of the control valve. But if we hadn't had dynamic simulation of this process, we would have missed that, I think, in the startup, and that's obviously saved us an awful lot of problems during startup. So that's a good example. This is an example of transferring from a storage tank fire pump direct, to a ship, storage tank to ship, beg your pardon. And the problem we have here is, of course, these are quite considerable flows to the ship. And in the event of an upset at the ship, they might want to close the valve off quickly. You have to have an automatic spillback set up. And basically this was developed to control spillback, and basically it helped us size the control valve, it helped us tune the control system, and that is the basis of the result, what we have here. So this is transfer flow rate to ship. This is the recirculation flow rate. And then we've got pump discharge and storage tank level. So you can see you can open up the simulation and look at any variable you want to look at, or you may have a problem with. So that's just an example of how you can use it for general processes without any measurements and process control issues. The next area we're going to address is the emergency relief. A case of external fire, distillation column, and a thermal runaway reaction. This slide you can look at when you get the recording of this, but just trying to show you a general one for a pharmaceutical plant where you have several reactors, receivers, a blowdown tank, maybe a scrubber, and just the different types that the ChemCAD sizing system can use. We've got rupture discs, we've got balanced relief valves, conventional relief valves, and that's just a little note about homogeneous equilibrium model, the ERM model, the H&E model. So really that's just a little introduction to the subject, but as you all know, it's a big topic. So the first one we're looking at is fire relief, external fire API 520, 2 tanks, and we have 2 separate set pressures. We've got the first one set at 250 psia. We've got a fixed nozzle size, and this one is set at 180 psia. It's a coincident fire, and what we have here's the pressure node, which balances the pressures during relief through the whole system. It's venting to atmosphere. This pressure node is set at a fixed pressure at 14.7 psi absolute, and these are the valve sections. Now we're looking at 2-phase flow here, and we've got Beggs and Brill, or you could use Baker, but I tend to use the Beggs and Brill. And that is basically what's happening. We can see here the pressure build up on the 180 psi one. You can see this one is relieving earlier, obviously, because of low set point. And then you've got the other one relieving later. And that's showing you the relief valve lifting and reseating again as the pressure dies off again, which is very normal on a process like this. Now we find this very useful because what it's now showing us is the flow regime in the discharge pipe work. So what we have here, the blue one, this is the water aspect of it. This is the gas, and then this is the total flow. Now, we found this invaluable because it enables us to size blowdown tanks, because there was a problem deciding how, if you have to allow for liquor and all this kind of consideration. So we found that invaluable for that. But there's far more interest now in two-phase flow, and this is a very powerful tool for demonstrating that. The next one is emergency relief on a distillation column. It's ethanol water. This is the conditions that we have for it. And basically what we're doing here, we're feeding fixed feed to a distillation column. We're ratioing the steam feed to the reboiler. We're doing level control on the reboiler at the bottom. We're doing level control on the reflux drum at the top. And basically what we're doing is we're measuring the composition here, and we're adjusting in cascade the distillate takeoff flow. So basically what's going to happen, we're going to run this at 1.5 bar, and then I'm going to drive the pressure at the top to relief pressure, which would simulate a blockage in the overhead situation. And this is what we get. So we've got the normal pressure running up to this time, and you can see what's happening here. Now, as soon as that pressure built up due to blockage or whatever reason, a valve was closed incorrectly, you can see that the reboiler duty drops right down, and the delta T is going down as well. That's because the pressure is going up, but the steam temperature hasn't changed. So that shows you that the duties drop down. And what we have here is the overhead and the supply to the condenser, obviously the same. But then as the relief valve lifted, the condenser flow dropped down. The total overhead flow didn't change because the balance of it was now going through the relief valve, which is this fella here. And then when the relief valve reseats again, you recover. And I think the thing to take away from this is that normally sizing relief valves, you would use maximum heat input to the unit. You would probably take the latent heat of the top and work out a sizing based on that. Now that's basically demonstrated to you that that valve will be oversized. So doing this approach, it gives you a better understanding of what's taking place in the column during relief. This was an example that we came across when we were doing a course. This is for hydrogen peroxide storage. And what we found was basically an undersized relief valve device in aqueous hydrogen peroxide led to initiating a thermal runaway. So what's essentially happening is what we're showing here, the red line here, is showing you a rupture disc which was undersized. So on the initial liftoff, it was fine. There was no problem. Look at the time here. This is external fire on time. But then it was allowed to continue running, and it wasn't relieving fast enough. So the pressure was building up. And of course, the temperature is going up, and that kicked off the thermal runaway reaction, and the vessel would have failed. So we then did a second run with a larger relief valve, and you can see it was okay. So I think that demonstrates to you, if you'd approach this from a purely steady state point of view, conventional relieving, you could easily have missed that. And the gentleman who was at the course, he was quite surprised when he saw that result. So that's something where dynamic simulation can alert you to something you might not have spotted. This is showing you the relief cases for the two situations. So now we're moving on to batch and continuous distillation. Dynamic simulation has an obvious use in the batch field, and we use it extensively for batch reactors, batch distillation. And we found it valuable for process development, equipment selection and control. But obviously it has obvious uses in the continuous distillation field as well. The Chem Stations have a unique unit which is just purely looking at the mass and energy balances of a batch distillation. And basically what it allows us to do, we can play with these parameters at the bottom of the batch still, and we can adjust these parameters at the top. And but you can really run different situations here. You can change the end step situations based on its condition and time, and you can manipulate all the variables you need in the batch distillation. But it allows you to come up with an optimization situation for the distillation. And this is the summary of the items you can get there. With the batch distillation, it's important you have a good understanding of the composition and the behavior of the components. And what we have here is an example of the residue curve, which is essentially what the residue curve is. If you start off with a batch still at this composition, this is telling you the line that this will follow as the distillation proceeds. The distillation we're looking at, that's the starting point here. And basically what it's saying, that's where we are in this region. So we can go anywhere in this region and have a successful distillation, but we can't cross over into this region because this is a zone. You can cross by adding precursors and things like that, but that's another matter. But this just to show you basically that the residue curve map is essential, and it gives you the identity of the azeotropes and the other conditions we have. This is the starting condition for the batch distillation we're looking at. And this is the summary of the distillation. We've essentially, ethyl acetate loss was 421 kilograms, and we had a 74% recovery. So what this unit actually does for us, it sets out the basic process in terms of numbers of steps, what cuts we're taking, what compositions we're changing the steps at. It gives us the basic operation. What we now have to do is select the appropriate equipment. And what we have here now is the batch reactor module, dynamic module. We've got the distillation column, and we have the reflux drum and receiver. And we're going to run the column with 12 theoretical stages, shell and tube condenser size to provide total condensation, and reheating medium is 12 bar. So this is just a straight run to see what equipment we're going to use to do the batch distillation we ran in the previous module. This is just to show you what the reactor looks like. We can do these various modes of operation, and we're invariably using specification of the system, but there's all these other modules that you can run it under. And this is just to give you an idea of the options that we have when we when we're identifying the requirements. That's the vessel size and spec details. And then this is the dynamic column. And this is just a summary of the results. Again, you can look at that when you've got the recording of this. And this is the results that we're getting. As I said earlier on, you can investigate if there's reboiler heat transfer. This is the still temperatures. This heat transfer coefficients we can look at. And we can also monitor viscosity. There's many parameters you can just open up and look for. This is now moving on to the control side of things. So basically what we have here, we've got the same setup with the vessel. We've got steam flow control on here now. We are going to control the top tray composition by monitoring its temperature. This is at constant pressure, of course. And so we're taking the temperature monitoring there. We're going to cascade that to a reflux valve and control the flow of the distillate to the receiver. For those of you not familiar with process control, what we're basically doing is we're measuring top temperature through a controller. We're measuring the flow to another controller, and this temperature is setting the set point of the master controller, which is just in the valve. So with a model like this, you can predict total cycle times. It helps you with control valve sizing. You can optimize parameters, and you can do controller tuning as well. And this is just a summary of the PID controller. So we set the range from 50 to 200. It's monitoring the temperature of stream 4. Its action is reverse. It's cascaded to controller 14. And here's the control settings that we can set. So we've got proportional band 100, integral time 5, derivative time 5. And there's the set point. This is the control valve. So it's got the CV, it's got rangeability, and it's a linear valve. And we can set the operational mode and the controller that it's going to. And I haven't mentioned ramps yet, but one of the most powerful features of ramps are that once you've got a simulation set up, you can put a ramp onto the flow sheet and you can adjust any variable either in flow or unit ops that you want to. And here we're adjusting the set point here, so you can see where we're driving things there. And this is the results. So here's the boil-up rate, and this is we can actually measure the composition in different stages, and this is the reflux ratio that was being controlled. This one has been calculated in Excel. This is an example of continuous distillation. We're distilling acetone, methanol, ethanol, water. We've got a dynamic column here, and we've got a control system controlling the pressure here. So what we're basically doing here, we're controlling top pressure by manipulating the cooling water flow. We are controlling the reboiler on level control, and we are controlling the steam on the temperature of a stage. So we've got a stage temperature here, we've got a lag introduced here, and this is cascading to the steam flow controller in cascade. So that's a full system control loop there. we've not done anything on the feed side here, but we could, here's a ramp here, which is adjusting feed as we want to. So we could do a step change here and see how the control system responded to a step change. We could do a feed change here and again see how it responds. This is just a summary. We actually got sieve trays here, and within the distillation module you can set up the reflux control setup, and you can set up the reboiler conditions and the top conditions actually within the same module. But I won't go into the details of that, but again you can look at that later. And this is the situation. So we're trying to control the set point at 180, which it did well initially. Then we hit it with a change, which it couldn't handle. Then it was starting to bring it back here. This is the set point of the pressure controller, and it was controlling at 760, and that was doing quite a good job there. This is bottoms composition, and this is distillate composition. So with batch reactors, we're going to look at jacket services, two types, indirect heat cool, and I'm going to show you a cryogenic reactor control system that we did, and measured parameters and scale up. We've used this module quite a lot in our work because we do a fair bit of work for pharmaceutical plants. There's different methods, just to summarize basically. That's the simple direct heat cool that you do. This one here is indirect heat, direct cool. So what I'm saying here is we've got direct cool this way, and then you've got indirect heat this way via a three-way valve. And then this one is direct heat, indirect cool. So in this case, we've got the chiller. And then here, we've got indirect heat, indirect cool. These invariably are using heat transfer fluids. So this particular is our preferred method, because if you get a breakthrough from any of these services into heat transfer fluid, as you probably all know, it can be quite difficult trying to source where the leak's coming from. At least if you have a reactor system, maybe you've got 10 reactors in the building, it enables you to isolate the leakage much quicker with that approach. So what we're showing here is an indirect heat with steam, indirect with steam and direct cooling with heat transfer oil. So what we have here is Siltherm XLT coming into a recirculating loop, this recirculating pump, three-way valve here. The beauty of this approach is that you avoid the lag in this heat exchanger, because when you're on full cool, you come in this way, and then you can come through here and you avoid the lag completely that can take place there. We're doing a cascade temperature control here, contents to the jacket temperature, jacket inlet temperature, and this is a flow control simulating the condensate removal system here, steam trap arrangement. And what we have, this is the set point that we're driving with a ramp. So we start off heating up from cold to a temperature. We then drop it back down to an operating temperature. Then we bring it back down again. And then this is the response. So the red line is the contents. So you can see it brought it up well, held it, and then pulled it back again, and then held it again, and then back again. And this is showing you the jacket temperatures. And this is the inside wall temperature here. And this is showing us the heat transfer coefficients that we're looking at. So you can really open the whole system up, and we found it invaluable for sizing the heat exchangers, pump circulation rates. There's a lot of interaction going on with a batch distillation jacket services, and particularly when you're looking at exothermic reactors. And it gives you a full cycle time. Sometimes we have to give guarantees about heat ups and cool down times, so we can check things of that nature. In the pharmaceutical industry, there's a lot of low temperature reactions taking place now, and we were asked to look at this particular system. Basically, we had Siltherm XLT at minus 90 degrees C, and they were doing reactions down to minus 50, minus 60. So there was a lot of concerns about sizing of the refrigeration unit. I'll just talk you through it. Basically, what we have here is, as before, we had a circulation system around. What we have here now is an electric heater. Obviously, we couldn't use steam here because we're going back from minus 50, minus 60. And this is controlled from Excel. So what we had is a temperature controller linking to Excel, and then we were calculating Excel the duty here, and that's how we controlled that heater. Through here into the reactor, return, and we recirculate. Now, when we went on to cooling, we feed in here, and when we feed in here, we have to return back here, and that is carried out here using a controller where we're controlling the balance in that loop. And what we have here, basically, if we just take it round, you come back with hot material. It's pretty typical of a refrigeration plant. You go into a hot side expansion tank. Here we're estimating heat gain, and this became very important on this job. It became as a surprise to people just how much heat was being lost, and it had a significant effect on the sizing of this fridge plant. We come to the hot side, and then we bring it back from the hot side through the fridge plant, which again was controlled by calculation from Excel using this controller here, to the hot side, sorry, to the cold side. And then the cold side would just recirculate round this way. So that would just recirculate round and balance. And then when we want to go into full cool, we went this way. So it was quite an involved situation, and the interactions we could study quite closely and come up with various considerations for design. And what I'm showing you here is the temperature profile. So this was cool down. This is the temperature of this Siltherm, and this is the contents and the wall temperature. This is showing you an indication of the duties. And one of the features which was quite powerful here was we could work out the ambient heat loss from the reactor. So we could set up the U, the area, and the ambient temperature. So we could set up the heat loss there. This is the little calculation that we were doing. It's not in entirety shown, but just to let you know that those controllers for the heater and the chiller plant were done from here. This particular job involved a half coil, and ChemCAD didn't have the facilities for working out the pressure drop across the half coil. So what we were doing here is working out the pressure drop through the half coil on the reactor. So you can see that the interface with Excel opens up a whole new area of opportunity for you. And basically, by doing this simulation, reactor cool down and heat up cycle times were predicted. we could do the simulation. We didn't mention that one with the heat loss protection, and the unit went online fine. If you have a simulation that's calibrated against a process, just give me a second. Yeah, if you've got a simulation calibrated and validated against a process, it can be used to obtain data for unmeasured parameters. And there was a plant in Sweden was having difficulty monitoring an emission with online analysis. And the calibrated simulations satisfied the regulatory authorities that it was accurately predicting the emission over the total operating range. And it allowed them to stop using the online measurement. So that was a tremendous bonus to this particular company because they're having a lot of trouble with the online measurement. So what I'm trying to show you here is that we've got a fermenter, and we're doing the fermentation of sugar in the presence of yeast, and we're feeding air in at that stage. We're measuring the inlet airflow, we're measuring the outlet airflow, so we know the oxygen uptake, but in this case we're not monitoring the dissolved oxygen level. So what I'm demonstrating to you is how, with a calibrated simulation, we can predict the dissolved oxygen level. And here we have the gas stream coming out of the fermenter. We've got the O2 uptake calculated in Excel. And here is the dissolved oxygen concentration. And it is quite normal to monitor the dissolved oxygen concentration, but it can become a troublesome measurement. And just to show you this, it opens up an opportunity to look at other variables as well. So in that case is the actual density of the broth. Fermentation scale up. This example, I had an example where they'd done the fermentation isothermally using this unitop. If you remember, you could do isothermal, and we wanted to scale it up, and the volume actually used in the isothermal was quite large. So we started off with a small scale 100-litre vessel, and this is the data that we had for that, and we found we had no problem controlling the temperature. But when we went to 8,000 litre, there was too much heat output that we couldn't remove. So it was a problem. Now, basically what it demonstrated was that something different than a jacketed vessel would have to be used if you were going to do it in that volume. It would handle a 5,000 litre vessel quite comfortably, but it certainly couldn't do anything above 8,000. And we can also predict power for agitation and things of that nature. So it's very useful for scale up from laboratory scale onwards. And this is showing you the 100-litre one. That's topping out at 31. That's not dropping off as quick as it looks if you look at the time scale. There's quite a long time scale there. But you can see that the 8,000 litre one, it got up to 50, which was not acceptable for the fermentation. And what I haven't really mentioned so far, within the reactor unitop, you can do detailed reactions, multiple reactions. And this is the reaction that we were doing here. We had 3 reactions going on: alpha glucose, nitrogen, and that was going to water. Then we had yeast and dead biomass. And then finally we had the alpha glucose, carbon dioxide going to ethanol. What we have found on occasions, and those of you who've been to HAZOPs, this comes away with some challenges, and invariably you either have to go away and do some sums, or someone with experience has the knowledge that allows you to answer a lot of the challenges that come from HAZOP. This system here was a situation where the client was making wash water, and he was making hot wash water or warm wash water with a heat exchanger. It was in the flue gas of a boiler. So basically what was happening, you were recirculating thermal oil around here, through there and back again, and you had wash water which was being circulated here and back there. And what happened, something went wrong somewhere and this vessel was overheated. You can see it's quite a big vessel, and it failed, and we were called in to take a look at the control system, and this is what we came up with. And it's there's quite a lot of interaction going on, because basically you've got them taking wash water off, you're making up with cold Towns water here continually because you're controlling level in this vessel. There's things happening on the boiler flue. There's the economizer is working here, so when the economizer is working, this temperature would be lower. But if for some reason or other the economizer was bypassed for some reason, then you would get a sudden change here, or could have. So there's quite a lot of variables taking place here. And essentially, we used a dynamic simulation to come up with the design, and which would enable us to size the valve, enable us to look at the response of the temperatures in the tank, and just general behavior. But it also enabled us to look at challenges. What happens if that valve failed open, for example? How quickly would this tank temperature go up? So this is basically what the challenges were. And what we've done here, we've again used the Excel situation. And what you find is you could do a simulation where you could put several ramps on, but if you want to synchronize what ramps are doing, it eventually becomes a lot easier to use a data matrix in Excel, which is what we're doing here. So essentially you've got the step times here. This is the boiler flue. So you can see what we're doing here. We're staying at 160 to 1380, then we're shooting it up to 221. This is the demin water. So what we can do is control various variables, and we could subject the simulation to various challenges, which is what we were doing. Like here's the valve being failed open, and so we can stress test the process. And just to show you one here, this is the control valve position here, and then we force it open, which is this here, and you can see the temperature. It's wash water storage got up to 90. This is with the valve failed full open and full heat on the flue gas, and this was the wash water loop. But you would say, well, that you could fail the vessel, but if you look how long it takes to get there, it took them 600 minutes to get there, 10 hours. So, you know, you could reassure people that if it does fail open, you're going to have high temperature alarms kicking in. Just to say the valve's jammed, you've got high temperature alarms kicking in, so there's plenty of opportunity for the process operator to put things right, to take the appropriate action. So that's a good example of how you can test HAZOP challenges. And this is just a general graph on the behavior of the plant. These have been generated in Excel, these graphs. So there's online applications and training. we do a fair bit on diesel blending. And what we have here is we're doing direct ship offload, and we're blending with methyl ester at various strengths, and we're going to storage tanks. The challenge here is that storage tanks, as you probably all know, can involve quite different distances on storage facilities. So the tank could be quite close, or it could be a long way away. So we're getting a variable back pressure here, which has to be taken account of. And we're doing, here's the methyl ester coming in through control valve, and here's the diesel flow coming in. So what we had to be sure of was that the pressure in this leg was always at a suitable point higher than the pressure in this leg, to make sure we transfer and we didn't get reverse flows or anything. And what basically we went with a 2-speed pump here, and in this case I was using a DP, a controller to do the DP control by adjusting this valve, and then we did the composition control using another controller. And just for training purposes, we developed a graphical user interface in Excel, which allowed the operator to just see how the simulation was working. And here that's the code there for the different values. So the blues inputs the simulation. This one is the results from simulation. So all these values in this color are coming from the simulation, and the other values are calculated. And we've got real-time graphs here from Excel. So you can do quite a lot in terms of training simulators just using Excel and the simulator. This is showing training simulators with online applications. You can link the simulator via data maps to SCADA using Excel DDE, which is not preferred. The OPC client is the best way. And this is not used as much as I think benefits could be gained from it. Because what you think about is that if you've got a calibrated simulation telling you the optimum operational points of a process, and you had those values displayed next door to the actual values running on the plant, you could see that it could be a great help to an operator on a process. We've done training simulators doing that, and it's with a training rig, and it worked quite well. But there's a lot of effort that goes into doing something like this. But just so that you know, this feature is available with dynamic simulation when it's linked to a process. And with training simulators, you can do all this kind of situation: operator responses, valve failure actions, pump shutdowns. So it can be very powerful. And there are companies that specialize in that sort of field. One of the things that I find very useful is training controller tuning. So with a very simple situation, you have a dynamic vessel where you're varying the flow into the vessel with a ramp. You're controlling the level here, and that's the PID controller, which you've seen before. So it's got a set point of 3. It's measuring the level in that tank, and we've got the tuning parameters here, and this is the setting for the ramp here, and we've got the control valve details. So what we can do with this simulator is check different control valve sizes, different control valve characteristics, we can play with the ramps, and it can be very useful for training purposes. And what I'm showing you here basically is the effect of the different parameters. So if you just have a proportional only controller at 25%, you'll see what happens is you'll get an offset and it'll control, but it will not return to set point. There will be a differential between set point and the actual value because you've got proportional only. If you narrow the proportional band, then the offset will not be as great because the gain's gone up. But now if you add integral action time, which is say 5 minutes, you'll see that what happens now, it'll go off, then it will bring it back to set point. And then if you do 2 minutes, it'll act faster, but you get little underrun, and then you get the action there. So it's really just to show you very simple simulations could be quite useful in training people to control, adjust tuning and everything on controllers. So in summary, why dynamic simulation? And I think hopefully we've demonstrated that there's good uses in the laboratory for scale up and helping the decisions regarding the experiments you do. In terms of design, it's very powerful on emergency relief, batch reactors, heat exchanger networks, and again, design, testing and troubleshooting. It can very quickly come to solutions in areas like that, and it gives you plenty of opportunity for considering optimizing process plant, operator training, and the calibrated simulation can be used for unmeasured variables. So in summary, timely identification of errors and weaknesses and testing of overall system performance, better understanding leading to reduced operator errors, increased safety and cost savings. And thank you for listening. That's just a summary there of some references. That was the reference, by the way, for the distillation column relief. And if you want to contact anybody at Chem Stations, there's your link. And if you have any separate questions, there's my link. And again, thank you for listening. I hope you found that useful.